All right, here we are for Honors Physics, Circular Motion, Universal Gravitation, Worksheet 1. We're going to take a look at problem 6, which is this problem with a Ferris wheel, right, going around a vertical circle. It says a 30-kilogram child is riding on a Ferris wheel that has a radius of 15 meters. The Ferris wheel turns in a vertical circle once around every 10 seconds, which is going to turn out to be actually pretty quick for a wheel of that size. Find the magnitude of a normal force that the seat applies to the child when they're at the top and at the bottom of the ride. Okay, so I'm going to make a quick sketch, and we're going to take a look at it when the child's at the top, when the child's at the bottom. So we're actually going to be doing kind of two separate calculations here, really. Two separate force diagrams and two separate calculations. So let me go ahead and sketch that out. So I'm going to do this one kind of like this. So I have the Ferris wheel, right? Okay. And we know that with a Ferris wheel, the little car that you ride around in actually is like suspended below the circle. And as you go around, you're actually going to travel in a path that is a circle. That's a terrible circle. But anyway, you're going around in a circle. That's a little better. Anyway, and the circle is the same as the circle of the wheel itself. You're just a little bit below. So the center of your path is actually like there, right? Anyway, now what we're doing is we're looking at forces on the rider, on the child that's on the ride, right? That 30-kilogram child. So when I go to figure out my forces on the person, all right, not on the car, but just the person sitting in the car, you say, well, ranged forces, there'll be gravity pulling down. I'm going to see that here too, right? Okay, and the gravitational force pulls down toward the center of the Earth. Now, the only thing touching the child is the seat that they're sitting on, right? That bench in the ride or whatever. And so that will be a normal force up on the child, right? And that's it, okay? If we're assuming that we're moving at a constant speed, then there's no need to have a force tangent to speed you up, right? While the ride is like getting going, you would have either a friction force from the seat, or maybe friction and a normal force from like the seat back pushing on you to kind of get you up to speed with the ride. But otherwise, once you're going around, you don't need a tangential force. So that's it. Again, the sketch that we drew here, we are looking, which you can see the circular path. So we are looking down the z-axis here. You notice that the forces we're looking at, these are in which axis? Well, here's the center of the circle. So this is like along a radius. This is the radial axis that we're seeing these forces in. There's no forces in the z, and tangential, we just talked about the fact we don't need one once we're going. So that's really it. That's our force diagrams. Let's take a look at the top of the ride, right? So here we go. If I go ahead and I do my sigma F equals ma, and of course the axis we're looking at is the radial. And so you say, okay, when I do this, I'll have forces, and you say, now I'm going to do the same thing when I'm at the bottom. So I'll be doing my sigma F equals ma, and we're doing, again, the radial axis. Now when I go to show my axes here, when I'm up here, right, we've got radial going up and down and tangential going left, right? You say, well, remember, right, and when I'm down here, I'm going to draw the axes like this. Okay, they kind of look the same at first glance, right? But there's a key difference, and that is when we do the radial axis, remember, in toward the center of the circle is always the positive direction. You don't have a choice. So in toward the center is going to be downwards, okay, in that radial axis. So the positive radial axis is downward. But here, in toward the center is upward. So upward will be the positive radial direction on this part of the diagram, on this part of the circle. This other axis is the tangential. I'm going to choose to call, if we're going clockwise, say in this picture, I mean, we could go from the other view from the other side, it would look like it was going counterclockwise. But if we're going around clockwise, then I'm just going to go ahead and choose to make positive like that way, in the direction of the velocity would be. All right, we're good with this, yeah? So what this means is when I go to write sigma f for that radial axis, it always has to be forces in minus forces out for the circle. So here it'll be mg minus n is mass times that acceleration, the radial. And acceleration of the radial we know is always centripetal toward the center. And when I do at the bottom though, it's going to be toward the center, in minus out again, but now in is normal forces in and gravitational forces out. Now, when I go to calculate AC, of course, I'm going to substitute in our equation for centripetal acceleration. We know that centripetal acceleration is v squared over r. So I can make that substitution. All right. So here's the thing. You say, hey, look, as we go around the circle, right, we are going around at a nice constant speed. That's the way Ferris wheels work, right? You're going around at a nice constant speed. So v is the same here and here, right? When we're at the top and we're at the bottom, it's the same speed, same tangential velocity. The radius of the circle, it's not changing. That's a constant. The mass of the child isn't changing, right? M and G aren't changing. So the only thing here, though, is mg minus n minus mg. You know that mg doesn't change, but somehow, right, mg minus n has to give me the same thing here that n minus mg gives me. And the only way that's going to happen, this side, remember, this is going to come out to be positive. Mass is positive, speed squared is positive, radius is positive, which means which has to be bigger here, mg or n, so that we get a positive answer out. We're like, well, mg's got to be the bigger number then, right? Bigger minus smaller give me a positive value. But here, n minus mg is this positive value. N has to be bigger than mg down here. So you recognize, hey, something's going on weird here. Here, n is smaller than mg. But down here, n is greater than mg. Right? And we're seeing that from this line. Because remember, this has to come out to be a positive value. Now, mg isn't going to change. How hard the Earth is pulling on you is not changing while you go around the circle. That normal force is going to have to be changing all the time while you're going around in the circle. Okay? Now, what we're trying to solve for here is, in fact, that normal force. Okay? At the top and at the bottom, it's going to be different for the two cases. Thinking about it, then just conceptually with the diagram, the total force has to be in toward the center. So mg had better be bigger than n here. But down here, the total force still has to be in toward the center, so n had better be bigger than mg down here. So let's so we're gonna have to do, well, two different calculations. Let's go ahead and give this a shot. Right, this one we'll just rearrange to get n by itself. So I recognize that I'm going to end up with n being equal to mg minus mv squared over r. With this one, getting n by itself, I'm just going to move the mg over. I'll have n is equal to mg plus mv squared over r. Right, see that little sign difference there. Okay, am I ready to plug in values and solve? And you say, well, not quite. Because they didn't, you say, I know m, right? It's 30 kilogram child. We know g, 9.8. We know the radius of the ride is 15 meters. But v, they didn't tell us how fast this person's traveling. What they did tell us is that it takes 10 seconds to go around once. So I'm going to do that calculation here kind of off to the side, if you don't mind. They told us that the period Okay, that capital T is the symbol I use for period. If I have something that is a repeating cycle, the time for one cycle we call the period. Okay, and that's 10 seconds. That's the time for this to go around once. The other thing we know is we know that the radius, they told us, was 15 meters. From this, we can find the speed. Okay, because we need to find the speed to put in there and put in there. I wish I didn't do that so close here because I wanted to put numbers in there. Oops, sorry about that. So when I do this, you say, well, I'm going to find the speed by saying that that's just the distance divided by the time. Okay, we know that when something is traveling along a curved path, it's hard sometimes to directly measure the speed. But the way we'll do is just look at the distance to go around once divided by the time to go around once. That's the distance to go around a circle once, that's the circumference. And the time to go around once, that's the period. So this is just going to be the distance around the circle, 2 pi r, divided by the time to go around once, the period. That will give me my speed. So for this case, 2 times pi times a radius of 15 meters, divided by the time of 10 seconds to go around. Punch that in my calculator. That's going to be 3 pi. And so when I calculate that, I get 9.42 about meters per second. So now I have a value that I can substitute in here and in here to solve for my normal force. So doing that little calculation, and yes, I'm going to try to squeeze it in here. That's going to be ugly, sorry. My normal force will be 30 kilogram child times 9.8 minus 30 kilogram child times that 9.42 squared, divided by my radius of 15. Okay. And when I punch that in the calculator, and I actually still have the answer there, so I'm just going to use that so I'm not dropping digits here. I got a value of 116.3 newtons. So that's the normal force when the child's at the top. And I'll do the same sort of thing down here with my values. 30 times 9.8 plus 30 times that 9.42 meters per second, divided by my radius of 15. So if I go ahead and do that calculation, 30 times 9.8 plus 30 times 9.42 squared. Yeah, see that one I'm having to truncate. Oh well. Divided by, round off rather, by 15. When I do that, I get, holy cow, that's huge, 471.5 newtons when I'm at the bottom of the loop. And so you say to yourself, look at that. There's a huge difference. That's a let me double check my math and make sure I didn't make a mistake sort of difference, right? Okay, that's huge. Yep. Okay, in how big that normal force is pressing on the child at the top and at the bottom. Quick. So that's the calculation part. Let's talk through significance of this a little bit. Okay. So the meaning of this normal force, I want to talk about that just a little bit. And that is, you'll remember, I hope, and this is tracking way back to the start of the year. Start of the year, what am I saying? I'm sorry, to the start of doing forces with, doing problems with unbalanced forces. We talked about the fact that we did this, the first problem we did with unbalanced forces was taking a look at a person in an elevator. And we talked about this idea of apparent weight or perceived weight, how heavy you feel like you are. We said, hey, if you're in an elevator, then the person in the elevator standing in that will have two forces acting on them. There'll be the gravitational force and a normal force from the floor. You say, hey, this looks a lot like this sort of situation, right? And we said, if that elevator is going to accelerate up, then you said those two forces aren't going to balance each other out, right? Because we need to have a net force up to make you, a total force up to make you accelerate up. So if we're accelerating up, then the normal force would better be bigger than gravity. And we said, what does it feel like to you when you're in an elevator that's accelerating up? Well, the floor, in normal situations, if you weren't accelerating, then those forces would balance out. And the floor would push on you with a force equal to your weight. Again, weight is the force gravity pulls with. That's your mass times 9.8, right? That's how hard the floor will be pressing against you. But now the floor presses up harder. It makes you perceive, then your brain doesn't really think about it that way. Your brain perceives that force pushing up on you, that's supporting your weight. Your brain detects that as being your weight. In other words, the gravitational force, the earth pulling on you, it's on you your entire life. It never goes away. And so your body is, it's always there. So your body, it basically ignores it. It treats it as being part of the background, and you don't detect it directly. You're not always feeling gravity tugging on you because it's always been there your entire life. And so you don't even notice it until it's gone, or something else weird happens. You're not going to feel that gravitational force. What you do feel is, like if you're sitting down watching this video, you're feeling the chair pushing up on you. And that force is really how you gauge your own weight, is that support force holding you up. So in this case, the floor pressing up is what you perceive, or what your weight appears to be to you. So if the elevator takes off up, the floor pushes harder, you feel like you're heavier. You feel like you think, it kind of makes you think like you're being pulled into that surface harder. Really, it's just the surface is accelerating up into you and pushing upward on you. On the other hand, we talked about if this elevator were to accelerate downward, then I need the force down to be bigger than the force up. Gravity doesn't change, so this normal force gets weaker and would be less than mg. And again, your body doesn't directly perceive mg, and so you're going to perceive that the floor isn't pushing on me as hard. I must be lighter now, is the way your body interprets that. You feel like you're lighter. So on this Ferris wheel, as you go around, we need the total force to be toward the center. When I'm at the top then, right, there's a certain amount of force inward I need to make me turn at that speed. So the normal force is going to get weaker so that I have that same total force, so that I keep up with that car, with the seat that's accelerating inward. When at the bottom, I need the total force to be up toward the center, which means N has to be bigger than mg, and that seat is pushing on me harder, like a lot harder. And so I feel like I'm really heavy because that seat is pressed into me so hard. Right? So apparent weight, you feel the heaviest at the bottom of the loop, and you feel the lightest at the top of the loop. Okay. And as a quick side note, hey, if you were waiting for the ride to get going, you're just sitting there, then that normal force and gravity, you're not accelerating anywhere if you're just sitting still. And so those forces would balance then if you're waiting for the ride to get started. And really quick, how big would that be? mg 30 times 9.8. So 294 newtons is your actual weight. And so you see, you feel lighter than your actual weight. Actual weight is just m times g. You're lighter than 294. I'm just going to jot that off to the side here. So you definitely feel way lighter when you're at the top, right? In fact, if it's going kind of fast, you almost kind of feel like you're going to go flying up off your seat. Now, a roller coaster, you definitely going over like the top of a hill, curving like that, you definitely feel like you're going to take off. This one, you definitely feel lighter, and you feel less connected to the seat, I would say, when you're at the top going over. And your kind of stomach kind of drops a little bit, kind of feels like, as you're going over the top of that curve. You might sometimes feel that sort of sensation going quickly over a hill in a car if you drive real quick. I'm going to talk more about that with a problem in the next homework set. but that sensation, you kind of feel like that. And you kind of feel like little butterflies in the stomach sort of feeling. At the bottom, whipping through, you feel like you're being pressed down into the seat a lot harder on that Ferris wheel. There's like a Ferris wheel at like Last Fling, not Last Fling. I'm sorry, that's in the fall. Usually in the past, at the start of the summer in June, Oswego has a Prairie Fest, they call it, and there's a nice Ferris wheel that they always have every year there, which is where I encounter a Ferris wheel every year. This last year in 2020, they had to cancel it, and I think this year they've pushed Prairie Fest to be in September, I think, for 2021. So I'm hoping to give this another whirl in the fall, so now I'm wondering, like, is that going to conflict with Last Fling that Naperville always has in September? I don't know. We'll see, or August. We'll see how that turns out. But anyway, yeah. So next time you're on a Ferris wheel, you might think about that and that sensation, and think about how heavy you feel like you are at the bottom and at the top. All right.